Welcome everyone. For today's prep, we're going to start looking at applied optimization problems. And this is going to take a lot of what we've seen so far with constrained optimization, all the techniques that we go into solving those types of problems, and finding critical numbers and classifying critical numbers. So all these different optimization techniques that we've seen. But now we're going to be putting those to use in more of an applied setting. And for the first example, we've got it right here. So let's read through it. So we're just going to do examples for these because it's really just putting together a lot of the different techniques we've seen so far. So for our first example, let's read through it. So we want to plant a rectangular garden along one side of a house with a fence on the other three sides. And we want to find the dimensions of the largest garden that can be enclosed using 40 feet of fence. Okay, so the one standout word here is largest. So that's an indication that we're dealing with an optimization problem. We want to find the maximum of something. Okay, so we know we have all those techniques, but when we're dealing with kind of problems like this, if we're dealing with something that we're building, it usually helps to draw a diagram. So before we get into all the math and everything, let's actually just draw a diagram of what we're dealing with here. So if we kind of go back through, you want to look for just keywords and phrases that describe the shape. What shape are you dealing with? And we see we're dealing with a rectangular garden. So to get things started, let's start by drawing a diagram. So I sometimes call this step 0. We want to draw a diagram for what's going on with the problem. So before we get to all the optimization stuff, let's get a diagram going. So we're dealing with a rectangle, so let's draw a rectangle here. And what we're doing is we're building this rectangular garden along one side of a house. So we have our rectangle here. So this is going to be our garden. And let's just pick one side, and that'll be the side where our house is. So let's say our house is over here. Okay. So there's our house. And the garden we're building is right here. Make it nice and green. Got a green garden. Okay. So, all right. What else are we doing? So we're putting a fence in along three sides of this garden. So we're doing a fence over here. We're doing a fence over here, and we're doing a fence over here. So each of those sides is getting a fence. And we only have 40 feet of fencing to work with. So as we're working on this, as we're drawing the diagram, we want to start to think about what is going to be the objective and what is going to be the constraint. And so we see that constant. We only have 40 feet of fencing to work with. So we can't make this garden as big as we want because we're kind of limited in how much fence we actually have. Okay, so we want to start to think about what is the objective and what is the constraint equation. So the objective, again, is the thing we're trying to maximize or minimize. So for this problem, we're trying to find the largest garden. So how do we measure the size of a garden? Well, we measure it with area. So area here is going to be the objective. So our objective is going to be the area. And then the constraint is, well, what you're limited by. So in this case, we're limited by how much fence that we actually have. Okay. And we know that is 40. Okay. So we want to start to think about then. We want to introduce some variables. And so for a rectangle, there's two different dimensions. There's the length and the width. So we can introduce the variables however we want to. So let's kind of use the traditional x and y. So we'll call this variable x, this length x, and we'll call this length y. So the length of this side of the rectangle is y. The length of this side is x. And with rectangles, opposite sides have the same length. So that means the other side is also length y. Okay. So what is the area of the rectangle? Well, area of a rectangle is just length times width. So for our problem, and the variables we introduced, that's going to be x times y. Now, how much fencing are we going to use? Well, we're only fencing 3 sides. So we're going to add up the length of fencing for this side, the amount of fencing we use for this side, and then the amount of fencing for the last side. So y here, the length of this side tells us actually how much fence we're going to use. So the length of this side tells us we're going to use a y section, a y amount of length there to fence in this side. Then we're going to use x number of feet to fence in the next side. So we'll add x. And then finally, to fence in that third side, it takes y amount of fencing. So we have y plus x plus y. And we can simplify that down to 2y plus x. All right, so we have our two equations. We have our objective equation. This is the thing we're trying to optimize, trying to find the maximum of. And then we have our constraint equation. This is the equation that puts some kind of restriction on what our variables can be. So now we're in a constrained optimization problem. So the difficult part with, a lot of times the most involved part with these is just getting these two equations set up, kind of reading through the problem and drawing the diagram and then getting the two equations all set up. All right, so now we kind of go through the motions. So we're going to solve this. So the next step is to solve the constraint equation for one of the variables. So whichever one's easier. So let's start with our constraint equation. 40 is equal to 2y plus x. And we have options. We could either solve this equation for y, which is not too bad, but it's even easier to solve this for x because we only have to move 2y to the other side. So in this case, it's slightly easier to solve this for x. And if we do that, we get x equal to, what, 40 minus 2y? Okay. And then once we have that constraint equation solved for one of the variables, then the next step is to plug that into our objective. So I'm going to shorten up our objective into a equals x times y, so just abbreviating that a for area. And we're going to take this objective and we're going to plug in. So wherever I see, in this case, wherever I see an x right here, I'm going to fill in what we actually know x is equal to. So in this case, it's the 40 minus 2y. So we're going to have 40 minus 2y in place of the x, and then times y. Okay. And again, we're just plugging in the constraint that we solved for. All right, so once we get it to this point, then now we have a one variable function. So one variable function, we know how to optimize this. So find and classify the critical numbers. So that's the next step. And we know that we're going to end up doing derivatives. So right now we have some multiplication here. So let's actually simplify just a little bit. And if we distribute this y, that'll kind of help us out a little bit. We end up with 40y minus 2y squared. And this version will be a little bit easier to kind of optimize. Okay, so if we want to, the next step, we want to find and classify our critical numbers. So we're going to start by finding the critical numbers. That's the usual thing we do. So how does that work? Well, we calculate the first derivative. So we're going to calculate a prime of y. And when we differentiate the first term, we get 40. And then derivative of that second term is minus 4y. So we end up with minus 4y. Okay. And then when we find the critical numbers, there's two ways we can have a critical number. Either it's equal to, the derivative is equal to 0, or the derivative is undefined. So let's start with this equal to 0. So sometimes you want to factor, but in this case, the derivative is simple enough where we can just directly solve it for y. So if we add 4y to both sides, we get 4y is equal to 40, and then divide by 4, and we get y is equal to 10. All right, so that's our critical number. Now, we could also have the first derivative being undefined, but that only really happens for us if we have division by 0 and there's no division. So we don't have a critical number that way. So the only critical number is this y equals 10. All right, so that's the first part of the optimization, the actual optimization here. Find the critical numbers. So if our garden is going to have a potential largest size, this is the only dimension for y that can give us that largest size. So we just want to actually verify then by classifying, do we have a maximum at this y value? So that's the next step. We're going to classify. So we're going to classify our critical numbers. Okay, so we have two options for how we do this. Either first derivative test, so we find the intervals of increase, decrease, and that tells us if we have a max or a min, or the second derivative test. And as usual, second derivative test is a little bit quicker. So let's start with that, see if that one works out. So let's try the second derivative test. So that means we need our second derivative. So if we calculate our second derivative, we'll call it a double prime. And we differentiate the 40, we get 0. Differentiate the minus 4y, we get negative 4. Okay. And the way we perform the second derivative test is we take our critical number that we found and we plug that into the second derivative. So we're going to evaluate the second derivative at y equals 10. And the way the second derivative works is it's a constant function. So no matter what number you plug in, you're always getting out negative 4. And the way we do the actual classification part is we think about what this means in terms of concavity. So negative second derivative means concave down. And then draw the concave down shape. And by drawing the shape, it kind of reminds you, well, we're going to have a high point. And that's precisely what the test says. So we have a local max at y equals 10. Okay. So we're just about done, but now we just want to make sure we actually answer the question. So let's go back up and let's make sure we actually answer what the question's asking us to find. So it says, find the dimensions of the largest garden. So a rectangle has 2 dimensions. So we found y, but we also need to find x. So we have a few ways we can do this. We can go back to our constraint equation, the original version we found. Or we have this nice version where we actually solve for x. So usually it's better to go back there. And we just plug in the y value that we found. So we found y equals 10. And we know x is equal to, what was it, 40 minus 2y. And so we're just going to evaluate that when y is equal to 10. So we get x is equal to 40, well, we can do that. If we plug in 10 here, we get negative 20. So we get 40 minus 20, which is 20. And we're done. Y equals 10, x equals 20. All right. So, well, we're not quite done. So we don't want to forget, especially with these applied type problems, if units are given, we want to include units in our answer. So let's see, are units given here? Well, yeah, they are. We're talking in terms of feet. So we just want to make sure that we specify the units for y are feet, and the units for x also feet. Okay, so we've answered the question. If we make our dimensions this size, we're going to have the largest possible garden using only 40 feet of fencing. And it makes sense that x here is bigger than y because if we go back up to our diagram, we kind of had to build two sides of length y, but we only had to build one side of length x. We kind of had this free side that we had against the house. So we only had to build one side of length x. So it makes sense then that that's going to be the bigger side. Kind of get a discount there. All right, so we're going to try a few more of these in class. So we'll see you then. Bye-bye.